Welcome back to Introduction to Machine Learning. I'm Ludwig Botmann, and in this video I will speak about splitting criteria for classification trees. At the end you should understand the different splitting criteria for classification, and you should know that there is a connection between empirical risk minimization and impurity minimization. As losses in classification, we typically use either the Breyer score or the log loss. Here on the slide you have the multi-class versions of Breyer score, which is basically L2 loss on probabilities. So taking the difference between the probability and the 0-1 coded class, squaring that and summing it up, overall classes, and the log loss, well, is the 0-1 coded class times the log of the probability, as we also use in logistic regression or in multinomial regression. The optimal constant predictions in a node are equal for both these losses, and are simply the proportions of the contained classes. So this optimal constant prediction, Cn, which for regression using the L2 loss was, for example, the mean, is here a vector of probabilities or of probability scores. So this vector has as many entries as there are classes in the target variable. We have G for the number of classes, and each entry of this constant prediction vector is just a proportion of the contained class. So for class K in node N, we compute the relative frequency of observations in that class. So we have a look at all the observations where the target variable equals the class that we have in the subscript of that p hat, sum those indicator functions up, and divide by the numbers of elements in this node. And we do this for all k in 1 to g, so that we end up with a vector of probability is here. Here we have a little visualization for you how this works. Let's say we have the Breyer score and try to find the optimal split. Okay, so what do? We try out different splits as for regression. Let's say we split at z-par length equals 5. We do not split at z-par width, but at z-par length. And then we can compute, or well, basically if we have split at z-par length equals 5, then we have two new sets, n1 and n2, that correspond to the nodes which we would have if we would split at z-par length equals 5. And then for both sets we can compute the optimal constant models. So what we have here on the left hand side is just the proportion of observations in those three classes for n1, and on the right hand side we have the same thing for n2. Okay, so for both sides of the split we just compute relative frequencies of the different classes, and that's basically it. Then for the risk, of course, as before, we have to sum up the losses with respect to those constant predictions in both nodes. We can do the same thing for a different split. For example, z-par length equals 6.5, and then again we can compute the class proportions in both resulting child nodes, so the left child and the right child, and then with those constant predictions, which are then those probability values, we can come up with the risk, which is again the sum of the losses. This will be done then for a grid of different values for z-par length, and we could also do it for a grid of values of z-par width, of course, but here we just focus on z-par length for a moment, and we compute for each split the constant predictions on the left hand side and on the right hand side, and with those predictions we compute the individual losses, sum those up, and have the risk. And then we just choose the optimal split point as being the split point which leads to the minimal risk, which in this case is z-par length equals 5.5. And of course, we could and should do the same thing for the other features too. So in that case for sepal width and those two other features of the iris dataset. Now there is a different notion that oftentimes is related to classification and regression trees. That's impurity, the Gini impurity or the entropy. And this is kind of equivalent, or it is equivalent to using empirical risk minimization. So the Breyer score is equivalent to Gini impurity. Here you have the formula for Gini impurity for data points in a node where we already have those optimal constant predictions. And log loss is equivalent to the entropy. So equivalent means that if we use log loss for deriving the optimal split, then we will end up in the same split as if we would use entropy. Perhaps as a small exercise for yourself, you can convince yourself that that will happen by just comparing the risk that results by using the log loss and the risk that results by using the entropy. And the same thing for Breyer score versus Gini impurity. So this means that trees can be understood completely through the lens of empirical risk minimization, and the new terminology of impurity is unnecessary at best and perhaps even confusing, so we will not speak too much about impurity here, but we will just stick to risk minimization. One last point here. Often we want to minimize the mean misclassification error in classification. So, or on the other hand, we want to optimize the accuracy, which is equivalent to minimizing the MCE. The loss that is used for this is the 0,1 loss. And one problem of the 0,1 loss usually is that it is not differentiable. But in this case, we do not care too much about that. So it's a non-issue, because in the tree optimization, we are having just those loops and we do not really try to differentiate here. So using 0,1 loss is totally okay for growing a tree. But Breyer score and log loss are more sensitive to changes in the node probabilities, and they often produce purer nodes and are, for this reason, still preferred over using 0,1 loss, even if 0,1 loss is possible. So let me explain this as a small example. We have some observations here which are divided in nodes N1 and N2 by one split, and into another nodes N1 and N2 by another split. And what you see here is that both splits, or with both splits, we end up in misclassifying 200 observations. So for the misclassification error, it really doesn't make a difference if we choose split 1 or split 2. But split 2 has purer nodes. Okay, so purer nodes means that this node N2 is pure in the sense that all the observations in that node belong to class 1, and not a single observation in node N2 for split 2 belongs to class 0. So that's a pure node, which is great, of course. And both Breyer score and log loss prefer this second split. So if using the mean misclassification error, there wouldn't be any difference between split 1 and split 2, because in both cases we have 200 misclassified observations. But if you use Breyer score or log loss, then we end up preferring the second split, which is good because, well, now we already have one pure node, N2, and perhaps in the next split we find something really good to split N1 further. So perhaps we have just with one further split a second pure node if we are lucky somehow. So we usually prefer using Breyer score or log loss over misclassification loss.